Hello, and thank you, Bronwyn, for the introduction. Today's talk will discuss the role of precision heat transfer as a component to optimize the performance of gels for surface cleaning, an aspect that has been under-researched and that has much potential. We all know that heat transfer is critical in structural conservation treatments. Both original and conservation materials require its use for successful results that cannot be achieved at room temperature. Even more so, we understand the importance of precision control. I would like to discuss the benefits of precision heat transfer, which has been made possible through development of carbon nanotechnology, which has opened new opportunities, including those discussed today in the specific context of gels. So today I'm going to talk about carbon nanotubes as innovative material for heat transfer, potential of precision heat transfer in enzymatic gels, testing of temperature-optimized gels, and some treatments. The gel-focused work discussed in this talk is a spin-off of research began in 2010 as IMAT project, which sought a radical improvement over the status quo for heat transfer by harnessing the electrical and thermal conductivity of carbon nanotubes. For those who may not be yet familiar with this relatively new familiar, nanotubes are one-atom thick tubes of graphene sheets made of carbon atoms to form a hexagonal lattice and are characterized by extremely low mass, extraordinary strength, and conductivity. We saw the innovation potential in the ability to apply carbon nanotubes to flexible textile substrates and generate uniform heat using ultra-low voltage. During the IMAT project, a heat transfer system was fully developed composed of flexible, transparent and breathable heating mats and control unit that generates ultra-steady heating with an accuracy of 0.1 Celsius. A description of the mats and the applications was presented last month at ICOM-CC in Copenhagen. One of the benefits of this project is the improved accuracy of heat transfer in the previously inaccessible lower temperature range of 25 to 50 Celsius, which in fact is a critical factor in optimizing enzymatic gel treatments. In real treatment conditions, the enzymes are highly inefficient since we force them to react with solid-state substrates, such as dried glue, starch, oil, and others. This is an unnatural environment for the enzymes, and their dynamics are restricted by limited diffusion. Beyond the customarily factors such as enzyme concentration, pH, conductivity, and ionic cofactors, a significant optimization can be achieved by accurately controlling the temperature, which has direct impact on the reaction rate, enzyme kinetics, diffusion, and intermolecular bonds, a dynamic that is well known but has not been exploited in art conservation in the past enough due to the absence of sufficiently precise heat transfer instrumentation. Enzymes have specific optimal temperature ranges. At room temperature 21 Celsius, alkylase 2.4L has only 15% of its activity and reaches 100% only at 60. Yet another important factor is the transport of the active content, water, enzymes, ions, which increases with the movement of the fluid and within the fluid. Temperature has a direct correlation with the diffusivity as seen on the graph on the right. In the recent study, we sought to verify the practical feasibility of temperature modulation to optimize cleaning dynamics in hydrogel and viscous gels. Samples of the pre-primed canvas were coated with rabbit skin glue tinted with carbon black. The blocks of 1.5% agar with 0.5% of alkylase 2.4 was placed on the tinted glue and left to dwell for 10 minutes at 8, 23.5 and 45 Celsius. The greatest increase of cleaning action as expected occurred at 45 degrees. The bottom image shows the cleaning action of agar with enzymes, bottom right, and without, bottom left at 45 degrees. The enzyme-free gel swelled but did not remove the substrate glue, while the 1% enzymatic gel effectively cleaned the surface. Many enzymes simply do not work at ambient temperatures or are at best extremely slow. Therefore, heat transfer, even at a minimal rise of only a few degrees, may already radically improve the cleaning action, as the samples above demonstrate, where the rabbit skin glue was removed at 29 Celsius, but the hydrogel with the same concentration of enzyme was not effective at 23.5 Celsius. A temperature-based approach was further tested to remove starch from paper using an alpha amylase band 480 and amplified 12L. The samples were stained with potassium iodide to assess the degree of cleaning under the different temperature conditions. In sample A, a higher concentration of enzymatic cleaning action was more effective, in contrast to the action of non-enzymatic hydrogel on the right sample A, which did not produce any cleaning action at 45 Celsius. Sample C below tested the use of very low concentration of enzymatic gels that can become effective, however, at already 0.025%, but at 45 Celsius. Another set of samples investigated the control of diffusivity of the active contact of the gel through the temperature control. The same enzymatic hydrogel was applied to the rector of the paper samples coated with starch on both sides. The active contact permeated the paper to also clean the verso at 45 Celsius right-hand side. However, the diffusivity may be suppressed by reducing the temperature as seen on the left side, where the cleaning action at low temperature was limited to the rector. At Lithuanian Art Museum in Vilnius, Lithuania, 8 glue residues were removed from 17th century prints seen here above. Alkalase 2.5L DX at 0.1% was used in 5% telos. The gel was applied on both sides of the print, which was covered with polypropylene film, and IMAT mat was wrapped to heat both sides. A similar approach below was applied to clean glue residues from textile using Everlase 16L and Esperase 8.0L. Temperature modulation was successful, removing glue residues on fragile surfaces of Edvard Munch paintings. Heat transfer allowed to substantially reduction of application time and made possible the removal of glue residues from water-sensitive surfaces. We also experimented a method of applying viscous enzymatic gels using warmed cotton swab wrapped around a heated needle, quite a handy method for small areas such as edges. Precision heat transfer was yet exploited in another way to clean the unvarnished porous surfaces of Vampire by Edvard Munch. Munch paintings consistently have very fragile surfaces due to his studio practices. To develop a safe cleaning method, we experimented with warmed agarose hydrogel applied by brush that also absorbed the soiling by capillary action and captured it within the solidified hydrogel. Prior to treatment, we tested warm agar on naturally aged and soiled canvas from 1940s at 70, 50, 40, and 35 Celsius for 1 minute. Counterintuitively, the cleaning action in this case was stronger at lower temperature, perhaps explained by the reduction of the agarose pore size at lower temperature that increased the capillary action. To clean the Vampire, we used 5% agar buffered ionic solution. We noted that it was crucial all the time to keep agar at the same temperature at the moment of application for repeatable results and even cleaning. Agarose was applied warm and was lifted for 1 minute, revealing the intact surface. To keep the agarose constant at 39 Celsius during the treatment, IMAT was wrapped around the beaker. In conclusion, enzymatic gels work most efficiently above room temperature, and precision heat transfer enhances their use. Nanotube-based heat transfer is precise enough and enough to be tailored for diverse gel cleaning scenarios. Minor temperature increase may yield dramatic improvement in cleaning action. Diffusivity can be controlled and increased using precision heat transfer, and inversely, cooling of the surface may be used to limit the cleaning action. Well, further research focused on accurate quantification of enzyme dynamics to include other enzymes is needed. Well, heat transfer can be used even as an alternative to solvent gels. In this case, for example, we removed pressure-sensitive tape from a collectible 1970 Luke Skywalker box from Star Wars. The surface was sensitive to solvents, and by placing mat under the paper substrate at 38 degrees, the adhesive was soft enough to allow a mechanical removal under the microscope. In practical advantages offered by the new warming technology, and approaches discussed today show the versatility of the new method and how easily it could be tailored to each case. New mobile accurate temperature instrumentation, the first letters which actually could be read as matte, we hope can be available within the next year. As conservators, we always wanted matte for our work, and in the meantime, IMAT prototypes are being experimented in the field. We welcome collaborations aimed to develop new treatment methods. And finishing, well, I may say, just may the matte and gels be with you. Well, thank you. Thank you very much for the attention, and I warmly thank you, my collaborators. Thank you.